alright, connected by link. The nodes are arranged in level in a hierarchical manner, alright. So remember our linear collections, alright, tree for example, list for example, stack or queue, it's a linear collections of element, isn't it? Alright. So tree is a collections of node, alright, which is connected by edges, or they are connected using link, right? Alright, the edge indicate relationship among the nodes. Top level is a single node called root. Okay, so this is how a tree will look like. Alright, so the A, B, C and so forth, all these are node, known as node. Alright, so top item, alright, it's known as a root. Okay, so here we're going to put the tree upside down. So root comes first, followed by the branches and leaves. Okay, so now we have root. Okay, and can you see this line here connecting to B? Node A connected to node B. This line is known as the edge. Right? So these are some of the terms you need to understand. So we have root, we have edges that connects all the nodes together. Then we have levels. So here this is top level, level 1. And in this tree we have 4 levels. So bottom part is the level 4. Alright? All this circle is known as nodes. All this alphabet is actually the data. Alright? Okay. Now, we can call A as a parent. Okay? And we can call the next level node as children of A. Alright? A is a parent. B, C, D, E is the children of A. Alright? And F, G, H, I, J, K, L, M is the grandchildren of the A. Alright? You understand? Of course, if I were to go down, I can say great-great-grandchildren. Okay? You understand that? Alright? So, H parent is C. C's child is H. Alright? So when I say parent, we have to go level up. Alright? When we say children, usually a level down. Alright? A is the root sitting on the top as a single node with no parent. Okay? If you have no parent, that is the root of the tree. Okay? Now B, C, D and E is known as sibling. Alright? Why sibling? Because connected to the same node. Okay? B, C, D are sibling because they are children of A and they are in the same level. Alright? Understand? Alright. Now F, I can cut F for example. This is known as a subtree for node B. Okay? Subtree of node B. Alright? And here we only have one node. Alright? Without no children. Okay? No children. No children means we call it as a leaf node. Alright? Here, no children. All these are leaves. Alright? Okay? Meaning you cannot store or there's no data after a leaf node. Right? Can you understand? That is the bottom, okay, of the hierarchy. Alright? So do you understand the concept? Simple thing you need to understand is the root, the nodes, okay, Where's the parent? Where's the children? Okay. Ancestors. Okay. Alright, we have ancestors. We know the top. Descendant. N is a descendant of A. Alright. So these are some of the terms you need to understand. Alright. Nodes at a given level are children of node of previous level. Alright. A node with the children is a parent node of those children. A node with the same parents are sibling. A node with no children is leaf node. Alright. The only node with no parent is the root node. Okay? Okay? So this is some of the terms. Okay? Now a node is reached from a root by path. Okay? So let's say if I want to access n. Alright? If I want to access n, alright, what is the way that I have to follow? What is the path? A, I have to follow to B, then F, and N. I cannot go from here and then jump over here and come back here. Alright, this one cannot. Okay, so this is the path, this is the connection that I have to follow. Alright, so this is known as path. Okay? The length of path is number of edges that it composes. Okay, so the number of edges that I have to follow. So the path is from here, follow the edges, okay, follow the link. Alright, okay? Alright, next is the height. Okay, height of the tree. The height of tree, let me explain here. Okay. Now, height of tree is, okay, 1 plus the height of the tallest subtree. Okay. Now, in this case, there are only one node. All right. So there's no children. So 1 plus 0. Okay. So the height is 1. So here I have the root node with 2 children. So the path is only 1. Okay. So 1 plus 1 is 2. That is the height. Okay. So from the root, go down to the last node. Alright. So we have 1 path here, then 1 path. Actually got 2, isn't it? Alright. So 2 plus 1 is 3. So this is the height of your tree. Okay? Alright, so do you understand subtree? The subtree of a node is a tree rooted at a child of that node. Okay? So for example, here. Alright, so this subtree, alright, belongs to B. Alright. So if I were to take this as a subtree, belongs to D. Alright. Okay. So of course if I were to take D, of course it has 3 subtrees. Alright, okay? So this is known as a subtree. This is similar to subarray, you know. Alright, so you just have a few data in it, okay? Alright, so that is terms, okay? Now terms usually doesn't come out in exam, explain what is the height and all that, alright? But you need to understand all this in order to understand the 3 concepts, okay? So now next, let's take a look at our tree. Binary tree. Binary means zeros and 1. Alright? Zeros and 1. 2 state only. So in that case, our tree, right, will have at most 2 children. Alright? 2 children. So one node will have at most 2 children. can have 0 children like M, O, no children, it's a leaf node. Or like L can have 1 children, alright? Or can be like Q or J or H can have 2 children. 1 child, no children, 1 child, or 2 children. Alright, do you understand? Can? Alright. Okay, so now usually we construct our binary tree like this. Your node will have our left connections, right? Or it can go to the right. Okay? So a tree will have a left branch or right branch. Okay? It can be empty. It can be only left, it can be only right, or it can be left or right. Okay? So for example, you can only have 1 node. Alright? You can have 1 node with the left branch only, or edge, or right only. Alright? Or you can have both sides. Okay? Empty. 1 child on the left, 1 child on the right, or you can have both child, that is left and right. Okay? And this is the height, right? Now when you have, let's say, this binary tree, okay? I have stored these alphabets in my tree, okay? If I have an array, for example, array, maybe I would have stored array like this, for example. Okay? Alright? If I have linked list, alright, I would have stored my data like this. This is H, this is I. So let's see. Example, this example only I'm giving. Alright? So this is how we store in array, this is how we store in linked list. How we store in binary tree is like this. Alright? Binary tree will be stored this way. Alright? Understand? Okay? So now, how to read it? How to read our array? How do you access the array? How do you read it? How do you traverse it? Of course, we have linked list, index, user. For array, you use an index. For linked list, usually you use first node, remember current node, yeah, to traverse, to access to the node. For array, use your index to access to your element. Is that correct? Alright. Now, for binary tree, in order to traverse, okay, tree traversal means the process of stepping through, visiting all the nodes in the tree. Okay, visiting the node. Right? We use the word traversal. We use the word visiting. Right? Visiting means what? Visiting a node means what? Is processing the data within the node. Alright? So just like an array, alright? So if I want to access to this, alright, I just refer to my array index. Correct? So exactly the same thing. In order to traverse the tree, we visit the nodes. Okay? Visiting a node means processing the data within the node. Right? Traversal can pass through a node without visiting at the moment. Alright? So you can just pass through. Alright? So for instance, alright, I want to access O only. Alright? So I can use the path from the root. Okay, imagine you have a path here. Okay, you just drive along the path to come here. Alright, do you understand? Okay, so we are not stopping anywhere. We are not processing I, we are not processing H. Okay, we only want to access home. Alright, for example. Alright, okay? So this is how we access. Alright? So this is just an analogy, but anyhow, for your traversal, there are 3 ways that we can access to our tree. One is pre-order traversal, another one is in order, and post-order. Alright? So let's see pre-order. We visit, understand when we say visit mean you process, okay? The route before processing the route, before, alright, the subtree. So you visit the root, visit all the nodes in the root's left subtree, and then only right subtree. Alright? So do you understand this? Yeah? Okay? Okay? So let's say, example, this is the left and right example. So I take the exam paper from here first. Okay? Alright? Here first. And then only I go to the right. Left first, then only right. Okay? Now even though on the left, if I walk this way, alright, I do have left and right, isn't it? Alright, if I walk this way. Alright, so what I have to do is that I have to collect all the left side first, and then go to the right side, finish already, then I go to the right side. Okay, Ken? Do you understand? Ken, alright, so I already written here, actually yesterday's class, pre-order, the rule is root, left and right. In order, left, root and right. And post order is left, right and root. Okay? So just check where you read your root. Process the root there. Alright, so now let's take a look at the diagram here. Pre-order, access this first. 1, 2, 3, 4, 5, 6. Come back up. 7, 8, 9, 10, 11. Alright? So if you go to in order, is between. So you visit your left subtree, then root, and choose the right subtree. Okay, so we go to all the way to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Alright, so if you don't understand this, raise your hand. I can explain again. And finally, we have post order, where we visit our root at the end after visiting all the subtrees. So you do your left and then right, and finally you go to your root. Alright? So take a look at the arrangement, the numbers, how we access to it. Alright? So beside this, we also can have level order, traversal, where each level, okay, you access the nodes. Okay? Alright, so let's try an exercise. Right? Easy exercise. So you have a tree. Alright? I give you 2 minutes, try it out. Okay? Then we will write the answers. Right, pre-order, root first, left and right. Okay? right? Okay, ready? Alright. So can you guys tell me the number for pre-order? 8, 3, 4, 5, 4, 10, 9, 7. Okay. 2, 3, 1, 8, 4, 5, 6, 11, 9, 10, 7. Okay, last one. 2, 1, 3, 4, 6, 5, 8, 9, 7, 10, 11. All right. Okay. So make sure you know how to do it. It's very important. Okay. Let's see whether the answer is correct. All right. Check the answer. Okay. Anyone don't know how to do this? Yeah? Can All right. So this is basically how you access to your data. Okay? You store the data. So you can either process it using a pre-order, in-order, or post-order. Right? So this is how you access to your hierarchical data. Right? Right? Okay. So next, let's do this. Right? So we're going to construct a binary tree using the traversal output. Okay? Now earlier, if you take a look at this, the tree is given to you, then you have to list down the order of traversal. Okay? Now, the order of traversal is given to you. Now you have to construct the tree. Okay? So this is something that we saw earlier on our questions. If you know how to do this, 10 marks easy. Alright? So then, yeah? Okay. How to do this pre-order traversal is given. In-order traversal is given. Okay? Many students go and draw 2, 3. I don't know how they came up with the 2, 3. Okay? It's just a 1 tree. We have to use both of this traversal in order to figure out what is the root, what is the left subtree, and right subtree. Okay? How do you do this? Alright? Now, we have to take a look at the traversal rules. Okay? On your traversal rules, you already know where is your root. On pre-order, root is in the beginning. On in order is in between. Post order is at the end. Alright? Now, if you take a look at your in order, alright, 5 can be a root, 2 also can be a root. So it's very difficult to determine our root using in order traversal. The only way we can determine our root is using pre-order or post-order. So given pre-order, our root will be the first number, first element. So pre-order, the first number is 6, correct? So 6 is your root, 6, alright? Now, of course, we need to have our left subtree and right subtree. Okay. Now, I know my in order. In between, I have a root. In the middle, whatever before is on my left subtree. Whatever after is my right subtree. So now I know my root is 6. Okay. So my root is 6. All this is my left subtree. All this is on my right subtree. Okay? So let's list it down. 1, 2, 3, 4, 5. Okay? It's on my left. 7, 9, 8, 10, 11 is on my right. Okay? So now root already decided. Our left subtree and right subtree is decided. So the next level, what is the children of 6 onto the left and the right? Okay? So what you do is, for pre-order, we will go through from here, from root, left and right. Okay, so let's take a look at the pre-order. So after number 6, if we were to read it this way, we have 4. Alright, so 4 is on the left. So this is 4. This will be the child of 6, and this will be on the left, this will be on the right. So on the left is 1, 2, 3, on the right is 5, only 1, I can write it like this. Alright, Ken? Okay, next number after 4 is 2. Alright? So after 4 is 2. So where's 2? 2 is here. So this is the child here. This is left. This is right. So there's only one element. I just write like this. So now left is done. Left is done. Now you have to do the right. Okay? So we finish with 4 done, 2 done, 1, 3, and 5 is done. Okay. Next number we have is 8. Alright, so let's go and check. Where is 8? 8 is on the right. Okay, this is 8. This will be on the left. This is on the right. So 7 and 9 and 10 and 11. Alright? So the next number is 7. Alright, 7 is here. Now, there's nothing on the left but there's one number on the right. Is that correct? Left is empty, right is number 9. Okay? Next is 10. So 10. So here you have 10. Okay. So there's nothing on the left. So right is 11. Alright? Okay? So this is how you draw, construct a binary tree using traversal order. Alright? Hannah? Alright, so now let's take a look at how to do it using our NetBeam. Alright? So of course, similar to any other editing, we have to create our interface. Alright? So let's take a look at the interface. Alright? Now for binary tree, we need to get root data. Alright? We need to check whether it's empty, is your tree is empty. Alright? We need to clear. We need to set the tree. Okay, we are setting the root data. And also we need to set the tree for the left. Okay? For the left tree as well as the right tree. Okay? The subtrees. Alright? Now, let's take a look at our binary class. Now, we have to use node to indicate the left tree or the right tree. Okay, I'll go here first now. Alright, so binary tree, we use a node to depict, alright, the left subtree, left child, and right child. Alright, so we need to create a node, okay, which has reference to the left child and also have reference to the right child, or it's basically a link to another node. Alright, so we must declare the nodes. Okay, earlier for our linked list, what we have? We have data, we have next. Remember? So here we must have left and right. So for example, okay, move forward a little bit. This is how it should look like. The nodes, alright? Okay? So it should able to point to the left nodes as well as the right node. Okay? Alright? So now let's go back. Alright, so to declare the nodes, go all the way down, just like our normal linked list node. We declare the left and right, okay? And we also get left, get right, and you can set the left node, and you also can set the right node, okay? Now, this one is to check whether you have a child, no leaf node, remember? Alright, so has left or not, has right or not, okay? So we have to check whether there's one child or two child. Leaf node mean left is null, alright, right is null, alright? And center, Okay, so that is other notes that you have to set. Okay. Now you also set your left tree and also right tree. Yeah. Okay. Now I want to show you is here. Now the sample code only provides post traversal. Okay. Pre-traversal and in order traversal, you have to do it for the lab class. Alright, so if you take a look at this, alright, our post order is left, right, and root. Okay, so you have to traverse, get your left node, and then get your right node, then only you read your root node. Okay, so if I were to write a code for pre-order, okay, so for pre-order you put your root on the top, okay, otherwise for in order your root will be in the middle like this. Alright, of course the rest of the things you have to change here. Alright, okay? Okay, so now let's take a look at the driver program. Okay, so first we're gonna construct the tree and then we're gonna check the post order traversal. Okay, so let me just run it first. Okay, the tree is constructing. Then you can see your root as well as your post order traversal. Alright, you can see. Alright, now let's check the code. Now what we're going to do here is that we're going to create we're going to create this tree. Okay, so now what we're going to do that, represent each of its leaves as a one node tree each. Okay, so we have tree D3, we set a tree with D. So we have D, F, G, and H. Alright, so each of it is a node, single node, not connected. Okay? And then, okay, we're going to create, set a tree for E. Now, E, alright, will have a left subtree and right subtree. Left is F tree and right is G. Okay, left is F tree, right is here, this is E. Alright, so now it's connected. Okay, next is B. B is D and E. Alright, so we have D, right? Sorry, B. B is E and D. So let me rewrite or redraw this. Alright, okay? So B is D on the left and E on the right. Okay? Now we have C. C is empty tree on the left. but H on the right. Okay, C. Alright, I have C empty here, H is here. Alright, it's not connected at all, huh? Alright, so finally we have A, alright, is connected to B and C. Right, so this is A, B, and C. So now the trees are connected. Alright, so if you go through course order, the value you will get is this. Alright, okay? Alright, so this is how we construct the tree using Java. Alright? Alright, another application for your binary tree is expression tree. Alright, the expression tree, alright, for instance, for prefix, infix, postfix. You remember we did this in chapter 1, alright? So in order traversal can be used for infix, pre-order traversal produce prefix, and post-order traversal produce postfix. For example, alright, let's take a look at prefix, okay? Alright, prefix. Let's take a look at this one, okay? So prefix, what do you have to use? Pre-order, isn't it? Right? So pre-order, what do we do? The rule is root, left, and right. Okay? Root, left, and right. Root, left, and right. Is this prefix expression? Prefix. Okay? Prefix, all your operator will be in front of the operand. You remember this? Okay? So let's take a look at this in terms of postfix. Postfix, left, right, and root. So what is my left? A. Okay? And then go to right, and finally only read the root. Correct? So is this a postfix expression? Yeah? Okay, so let's read this as in order. Okay? In order means infix. Okay? The operator is in between the operand, just like this one. Alright? So we read left, A, then we read the root, divide, and then we read the right. So this is in order, infix, this is post order, postfix, this is pre-order, prefix. Alright? Okay? So the algorithm, okay? So first you read the first operand by evaluating your left subtree. Second operand will be on the right subtree. Your operator will be on the root. And of course you use your operator, your operands, first and second operand to perform the calculation and return the results. Okay? You also can use it for decision-making tree. Decision tree, alright, for expert system, for example, alright, if there are problems, you have to make a decision in terms of yes and no. For example, here is the picture clear? Yes? What do you do? No mean what do you do? Alright, so again, this is also in terms of binary tree. Alright, you have to store the data in terms of a binary tree. Okay? Alright, next. Okay, guessing game. Also, you can use binary tree, alright? So for example, if you want to guess the country, so you can ask a question in terms of, is it in the North America? Yes, me. And then you guess it, correct or no. Okay? This is examples. Alright? Now, earlier I showed you our traversal. Okay, traversal, remember? Alright, so we want to check our node is not now, then you get your left subtree element, get the left node's data, then your right node data, and then after that your root. Okay, so here, alright, we can use a recursive method. Alright, best thing to use to access our binary tree is the recursive method. Alright, because recursively we have to go and find the last element, isn't it? Alright, so that is the best method to use using recursive. Alright, so please during your practical class, try the code for infix, in order and pre-order. Alright, now besides using this, we also can use the iterator to access to our data. Alright, remember iterator or not allows us to visit the element in your collections without removing them. Alright, and of course it gives you more functions. Alright, okay, so it's similar construction as in your link structure. Alright, so binary nodes I already explained to you. Alright, next thing is let's take a look at binary search. Okay, binary search. What is the binary search? What is the search? You remember search or not? Alright. Okay, to locate our data. Alright. So in order to do that, we have to use a comparable. Right? Now if you take a look at this tree, for example, right? Okay, I have Jared. Okay, now if you take a look at the left subtree, all right, all the alphabets, all right, starting alphabets all are lesser than Jared. Okay, and on the right is all bigger, all right, more. Okay, or after J. Alright, so this, in order to have a binary search tree, alright, so we have to make sure our data are arranged accordingly. Alright, so we have to use comparable. Alright, so do you remember comparable for sorted list? Okay, remember? So similar to that. Okay, now let's see how we're going to do this. Now I'm going to show you the code. Alright. Okay, I'm going to run this binary search. Okay. So if there's an entry, alright, we have to compare to, alright, to find the entry. Okay, so we compare. If I'm looking for an entry, alright, so if it's equal, of course I return the result plus the data. Otherwise I compare and I go to the left side or to the right subtree. Okay, so now let's take a look at an example here. Okay. Alright. So here, first let's add the element. So you have this binary tree, Jared, okay, as a root node. We want to add chat in. Okay, chat is C. So when we compare with our tree, start from Jared, chat is C, right? So C is in front of J or after. Okay, all right. So since it's in front, so now we have to compare with the subtree. All right. So again, C here, B. All right. So I cannot put it on the left subtree. I have to take it to the right subtree. Okay. So now once goes to the right subtree, even though there's only one node, I need to check with Doug, C and D. Alright, so C comes first or D comes first? It should go on the left side or the right side? Left or right? Left, okay? And then only we add the value. Okay, how we can do this? But of course by using compare to. Alright, we talked about compare to before, comparable, huh? Right? So this is how we recursively add the value, right? So we use add entry, find entry, then add entries, huh? Recursively we can use this, okay? So these are the functions. Normally you can just add into a particular locations. In this case, we have to check, compare first. You have to compare first before you can add. Alright? So suppose you have a duplicate entry. Alright? Suppose you have a duplicate entry. How are we going to add? Okay? So again, of course, we have to check whether it's greater than, lesser than, or equal, isn't it? If it's equal, then what do? Alright? So of course, we move to the right subtree. Okay? But once we move to, we want to insert Jared again. Right? So we move to the right subtree, then we have to compare with Megan, then compare with Jim, then only we can add. We cannot simply add Jared here. Alright? Okay? So that's how tree works. Okay? Now, okay? So first, let's do this question. This is binary search tree. Let's construct the binary tree. Okay. How to construct the binary tree? Now you must know your ABCs, right? So first element you have here, first data is M. So M will be your root. Okay? Now what is my next element? E. Alright? So I compare E and M. Greater or lesser? Alright? Lesser, right? So go to the left. Okay? Now we have Q compared to M. Greater or lesser? Greater. Okay? Then go to the right. Okay? Next, what we do? W. Okay? Can you construct for me? I give you 2 minutes. alphabets. Follow the alphabetical order. Greater or lesser start from M, start from the root. Okay? Alright? Okay, compare. Okay, got it? Now, can you do pre-order, in order, and post-order? Okay, try it out. Alright, so your questions to draw the tree, to add and remove. Alright? Okay, so this is for your pre-order, post-order, in order. Now please make sure you know how to do this. Not just take picture and forget about it, huh? Alright, now next thing that I want to go through is to remove entries. Earlier we learned how to add, okay? Now we want to remove, okay? Now, how to remove? Alright? To remove, there are three possible ways or cases you will come across, right? And then you must figure out how to remove it, right? How do you remove when you have a note with no children, right? How do you remove a note when you have one child, okay? How do you remove a note with two children? So for example, right, say I have a note here. For example, right, if I want to remove a note with no children, a leaf note, how do you remove it? Okay, so I can just remove it. Alright? Okay? Okay, how do I remove a note with one child? Okay, I remove a note with one child. Now this child is orphan. The data is lost. Alright, so for an analogy, my parents died already. I'm a baby, example. Right? So who need to take care of me? Right? Grandparents are? Yeah? So what do? Link to the grandparents. Okay? But got two children. Okay? Here, E got two children. If you remove E, 1, 2, 3 data is lost. Okay, how to put both to the grandparent? Binary 3 must only have 2, right? Okay, so how? Right? How to link? Alright, so these are the 3 possible cases. First case, right? Show you the easy one. Right? First case, we want to remove the leaf node, just remove it, and this is your final tree. Okay? When you have a single child, a node with 1 child, okay? 18 got only 21, 1 child. What do? You connect the child to the grandparent. Okay? See? So, any question here? Alright? Now, but when you remove a node with 2 children, let's say we have 12. Alright? How do I connect them? You can choose a left subtree or you can go to the right subtree. 2 ways of doing it. Alright? Now, if you are selecting left subtree, okay, if you are going to the left, you must choose the largest value. Left, large value. So we go to the left. Okay, that's only 1 child anyhow. Alright? What do? You take number 9, you replace it. Alright? 12 with number 9. So 9 now become the parent. Alright? Okay? So it's like assuming me and my brother, okay? My brother will become the parent of me, okay? For example. But here you have to select. If you go to the left subtree, select the largest value. Alright? Largest value. So suppose if we have, okay? Suppose if we had 8 here, then here you have, let's say 11. On the right we have 11. Okay, so you have to choose 11, no more number 9. So because the largest node there is 11. Alright, so in this case we only have 1 node, so we can choose 9. Okay, now if you go and select your right subarray, so if you go this way now, alright, we have to select the smallest value. So here in this node 21, 25, 19, the smallest value is 19. So take 19 and replace it. Alright, 12 replace with 19. Okay. Alright, so this is how your tree will look. Alright, remember you can take the left subtree, okay, choose the largest value, or you can take the right subtree, choose the smallest value. Now let's take a look at our tree, okay. Now this is the binary search tree. As such, right, sometimes it has to be balanced, okay, all right, it has to be balanced, okay. How? It's like this, okay. Now if I remove 1 child here, 18, you can see 5 and 21. 21 is more than 5 enough. Alright, so it's in correct position. Alright, okay? Here. here, when I put 9 up here, 9 is more than 5, correct? Okay, logically it's correct. Alright, and then 21, of course, more than 9, and it is sitting on the right side. Okay, right subtree. Correct? Okay, now here, when I choose the smallest, okay, now I put 19 up. Alright, so is 9 less than 19? Okay, is 9 is less than 19, which is on the left side, correct? 21 is more than 19, so it's in the right side. So now the tree is correct. Okay, so when you redraw it, make sure you count and see, is it correct or not correct? Okay, binary tree will work like that. Okay. Alright, so this is the code for it. Okay, now finally, let's try to remove. Remove A, just remove lah. Remove Q, W will link to M. Okay, remove E. Okay, E. So this one is gone, this one is gone. So you have E. We need to remove E. E got 2 children, C and H. What will replace E if I choose a left subtree? D. If I choose a right subtree, smallest G. Okay, so here, okay, this is the answer. Wait, I'll give you the whole answer. Okay, so that's just how it should look like. This is, we are choosing the left subtree. Okay, you can do the same thing with your right subtree also. Okay, so this is the answer, the last answer. Alright, if I were to move to, or if I go to the right subtree, then this is how it should look like. Okay? Alright, that's it. Okay? So please go through it. The rest is alright. Okay, this is other structures, other trees that you can go through. Okay, now let's just revisit the question. Okay, so both you can do, Alright, so try this one out. Alright, try it. How your tree is gonna be. Now it's a post order. Earlier we did a pre-order. Post. So what we should. Hello? Can hear? Okay. Your post order, okay? Your root is at the end. So your root is 1. Okay? So you have to read from here to here. Okay? Do you think I can draw it? Okay, tell me here. Okay, 1 is the root. Okay, so left, right. Mana-mana? Okay, next number is 3. Where do I put? Where the 3 should go? Okay, so you have to read from root to right. Okay, so number 1, 4, 8, 2, 5 is here. 6, 3, 7 is this side. So the next number is 3, 6, 7. Is that correct? Next is 2. This is a binary tree, it's not a binary search tree. So as such, you can see 8 is sitting somewhere on the left. Okay, now let's remove 3. How do you remove 3? Got 2 children. Okay? How can we remove? Okay, of course you have to redraw this again. So it could be 7, 6. Alright? You have to redraw the whole thing again, huh? Okay? Or it can be 6, 7. Right? Okay, how are you going to add 5? 5 is already there. 5 is here. Okay, do you add 5 here? Okay, suppose if I were to choose this 7, how do I add 5? A lot of students make mistake here. Okay, 5 here. Can I add 5 like this? No. Add, sorry. Okay, 5, check, less or more. Come here, 5, check, less or more. Check, less or more. Less or more. Okay? Okay, similarly you can do this question. It's quite easy to score marks here, right? It's very easy. You just have to draw. Know how to do it. No need to revise a lot. Okay? So you can put a lot of effort for question 3, coding question. Okay? So this is similar one where you have to add 75, then remove 70. You may have a single